Welcome! In this differential equations tutorial, we're going to solve some very basic differential equations, both separable and linear, and we're going to look at some examples of solving differential equations, but of the applied variety. For example, this question 4 is about carbon-14 and the radioactive decay of carbon-14. So if you're interested in this sort of thing, then stay tuned. All right, let's get into the first problem. So it says, give the general solution of each of the following ODEs. Now, ODE is short for ordinary differential equation. So we have 2x dash plus 3 equals 0. Now, this one is separable, so we can take the 3 over to the right-hand side and then divide throughout by 2. So we have dx on dt is minus 3 over 2. Okay, now we said this one's separable, so we can take the dt over to the right-hand side, put integral signs on these, and then integrate. So on the right hand side, we have minus 3 over 2t plus c. On the left hand side, we just have the integral of 1 with respect to x, which is x. There's a plus c there too, but c1 minus c2 is just another c, so we only put one c there. Okay, so we've solved this differential equation. Now in question 1b, we have 2x dash plus 3x is 0. So we take the 3x over to the right hand side, and so we'll get 2x dash equals minus 3x. Now let's divide throughout by 2. So we have dx on dt is minus 3 over 2x. Okay, now this one is separable. It's also linear, but via separable methods, we want to divide by x to put the x with the x and the t with the t. So on the left, we have the integral 1 over x with respect to x. And on the right-hand side, we have the integral of, that should be minus 3 over 2 with respect to t. Okay, so let's finish this off. The left-hand side is the natural log of x, and the right-hand side is minus 3 over 2t and plus c. Okay, now we just have to solve this for x. So x is equal to e to the power of minus 3 over 2t plus c. And using exponent rules, we can break this up as e to the power of c times e to the power of minus 3 over 2t. Now, e is a constant, c is a constant, so e to the power of c is a constant. Let's name that a. So we have x is a function of t. It's a e to the minus 3 over 2t. Okay, that's via separable methods because it is a separable equation. It's also a linear equation, so let's also solve this using methods for linear equations. So we have 2x dash plus 3x is 0. And so dividing throughout by 2, we have dx on dt plus 3 over 2x is 0. Now, x is the dependent variable, and so we have this in the form to recognize this as a linear differential equation. So we multiply by the integrating factor, and so it's a function of t, e to the power of the integral of 3 over 2 dt, which is e to the power of 3 over 2t. Okay, so we multiply by this integrating factor, and we have e to the 3 over 2t dx on dt plus 3 over 2 e to the 3 over 2t times x equals 0 times this integrating factor, which is 0. Now, the left-hand side packs up using the product rule into reverse, because if we were to differentiate the product of e to the 3 over 2t times x, this is exactly what we would get using the product rule. Okay, so this is the product rule. Okay, so now that we have this equation, it is now separable, and so let's separate it. So we have the integral of 1 with respect to this product is the integral of 0 with respect to t. So integrating the left-hand side is easy. We just have what's inside the bracket, and on the right-hand side, we have a constant. Let's call it a, because I know how this is going to work out. Okay, so to finish this off, we just divide by this, and we have x as a function of t is a e to the minus 3 over 2t. Now, is this what we got using the other method? Yes, it's exactly what we got. Okay, fantastic. Let's move on to question 1c, and keep those solutions handy because question 2 has the same differential equations but adds on initial values. Question 1, part C, we have 3p dash is p. So we want to divide throughout by 3 because this equation is separable. So dp on dt is 1/3 p. So let's divide this by P, putting the P with the P and the T with the T. Okay, so now we've separated it. It just remains to integrate and then solve for P. So we have natural log of P is 1/3 T plus some constant, say C. Okay, solving this for P, we have P equals e to the 1/3 T plus C. And so that's e to the C times e to the 1/3 T. Again, let's name e to the C, let's call it A. So P as a function of T is A, e to the 1/3 T. Okay, and we finished that. So now let's move on to the initial value problems in question 2. Keep these solutions handy. Okay, so in question 2, referring to question 1a, we have x as a function of t is -3/2 t plus c. And up here we have an initial value. That initial value allows you to sub these numbers in and find out what c is. So this says when t is 0, x is equal to 1. So 1 is equal to x of 0, which is -3/2 times 0 plus c. So since this is 0, this says c is equal to 1. And so we get then x of t is -3/2t plus 1 plus 1. Okay, so now let's move on to 2b. So in 2b, we have 2x dash plus 3x equals 0 with x of 4 equal to 2. Now, from question 1b, we got x of t is a e to the -3/2t. So we want to use x of 4 is 2 to find out what a is. Now that says when t is equal to 4, x is equal to 2. All right, simplifying this, 4 divided by 2 is 2. So in the exponent, we have -3 times 2, which is -6. So a e to the -6 is equal to 2. And multiplying throughout by e to the 6th, we have a is equal to 2 e to the power of 6. Okay, so coming back to this line, x of t is 2 e to the 6 times e to the -3/2t, and we can write this x of t is 2 e to the power of 6 -3/2t. Okay, great. Let's move on to question 2c. P of 0 is P of plus P of 6 is 2. Now in question 1c, we got P of t is a e to the 1/3 t. So subbing in 0 for t, P of 0 is a e to the 0, which is a. Okay, now subbing in 6, P of 6 is a e to the power of 1/3 times 6. Now 6/3 is 2. We have a e to the power of 2. Okay, this relation up here says if we add these two together, then we should get 2. So a plus a e to the power of 2 is 2. We can factorize the a out on the left and then divide by 1 plus e squared to get the value of a. Okay, so now that we have a, let's substitute this into this line. So we have P of t is 2/1 plus e squared e to the power of 1/3 t. Okay, moving on to question 3. State the order of each of the following ODEs. So in question 3a, if we were to take this 7x double dash to the left-hand side, we have this. Now, the order of this is the greatest number of derivatives or greatest number of times x is differentiated with respect to t, and that's 3. So the order of the equation is 3. Okay, is it linear or non-linear? Well, it's linear because everywhere the derivative appears, it's to the power of 1. It doesn't appear in a nonlinear function. It appears in a linear function. So x triple dash is just on its own. It does not get squared. It does not have a sign or a cos in it. And the same for these. So this is third order linear. All right, so question 3b. So let's have a look at this differential equation. It has a second order derivative in it. That's the highest order derivative that appears in the equation. That's 2. So the differential equation is of order 2. Have a look here. This first derivative is getting squared, and so squaring is a nonlinear function. Second order nonlinear ODE. All the derivatives that appear are ordinary. They're not partial derivatives. They're ordinary derivatives. Okay, so in question 3c, we have a second order differential equation because the highest order derivative is 2. It's nonlinear because these derivatives appear in nonlinear functions. So this is a second order nonlinear ODE. Okay, question 4. Radioactive carbon-14 is present in small quantities in all living matter and is constantly replenished from the atmosphere. when an organism dies, the carbon-14 decays to stable carbon-12. Suppose that C of T is the mass of carbon-14 measured in grams, present in a sample of bone at time t, measured in years. The radioactive decay is described by the differential equation. dC on dt is minus K times C. So that's minus a constant times C. It is a little bit unfortunate that we have chosen an uppercase C to be that dependent variable, but let's live with it. Okay, so if the half-life of the decay is 5,730 years, calculate the relative rate of decay K to 3 significant figures. All right, so what this says is half of the amount is present after 5,730 years. So this says C of 5730 is 1/2 C of 0. With this, let's just write this as C of T is 1/2 C of 0, where T is 5730, just so we don't have to keep rewriting this 5730. Okay, and so here then we know the solution to this differential equation is C of T is AE to the minus KT. All right, so this equation is separable, and this is what the solution will look like. Then on the left-hand side, we have AE to the minus KT, and on the right-hand side, we have 1/2 AE to the minus K times 0. And so that exponent is 0, so e to the 0 is 1, and so we have 1/2 A. Okay, so with this, you can see we have an A on the right-hand side and an A on the left-hand side, and so if that A is non-zero, then they can just cancel. And so from this, we'll get 2 is equal to e to the KT, okay, having multiplied both sides by 2 and multiplied both sides by e to the KT. So solving this equation for KT, because we want to solve for K, so we have KT is equal to the natural log of 2. And so K then is equal to 1 over T, but T is 5730. So 1 over 5730 times the natural log of 2. Okay, and so we've answered question 4A. We found the relative rate of decay K, but we haven't done that to 3 significant figures. So let's open up Mathematica and calculate this. Okay, so I'll just write in log. Now, when I write in log here, that is the natural log. So log of 2.0, and then let's divide that by 5730. Okay, and so we can say that this is approximately 0.0012096, and so on. Okay, but we want to write this to, what is it, 3 significant figures. So let's go back to the question. 3 significant figures. There we go. So writing this to 3 significant figures, we would just take the first 3, rounding that fourth one up. K equals 1.21 times 10 to the power of minus 4, because this is 4 decimal places over. 1, 2, 3, 4. Okay, there we go. So now we've done question 4A. Okay, next it says in January this year, a team of scientists found a human bone fragment which contained 89% of the carbon-14 contained in living human bone. How old is the bone fragment? Okay, so this says that C of T is 0.89 C of 0, and we want to solve this equation for T. Now on the left, we have AE to the minus KT is 0.89. C of 0 is just A, so 0.89A. Okay, and so this gives us e to the minus KT is 0.89. Now we already know the value of K. It's given up here. So taking logs, we have minus KT equals the natural log of 0.89. So dividing by minus K, T is minus 1 over K, natural log of 0.89. Now there's a log rule that says that we can take this minus 1 up into the exponent there. So then we have natural log of 1 over 0.89 over k, where k is 1.21 times 10 to the minus 4. Okay, so back to Mathematica here. Okay, so there's our k value. So let's just enter that into memory. And then we want to take the natural log of 1 over 0.89 and then divide that result by k. So what we get then is that t is 963.089 years. Okay, so let's go back to our question. How old is the bone fragment? Okay, so given that this is given to 3 significant figures, the convention is to write this to 3 significant figures also. But again, it's just a convention. Okay, question 5. 2 researchers are investigating the metabolism of a new drug. Let D of T represent the amount of drug at a particular time T. The initial amount of drug is 100 grams. After 1 hour, the amount is 75 grams. Researcher A believes the drug behaves like alcohol and decays linearly. Write down an ODE that describes this behavior. Give its general solution and use the information to determine the rate of decay. All right. So what we have then in question 5 is D of 0 is 100 grams and D of 1, because that's after 1 hour, is 75 grams. Okay, so if we had linear decay, then we would have D dash of T is minus B, where B is a positive number. Okay, so solving this gives us D of T is the integral of D dash of T with respect to T. And so the integral of minus B with respect to T. So then we get minus BT plus a constant C is D of T. Now, D of 0 is 100 grams. So let's say since D of 0 is 100, we have then 100 is equal to D of 0, which is minus B times 0 plus C. So this gives us a way to find C. Now minus B times 0 is 0, so this says C is 100. And so what we get then is D of T is equal to minus B of T plus 100. Okay, so next, D of 1 hour is 75. We have 75 is equal to minus B times 1 plus C, but C we found out is 100. So this gives us a way to find B. So on the right-hand side, we have minus B plus 100. So taking that over to the left-hand side, we have B equals 100 minus 75, which is 25. So B is 25. And so linear decay assumption gives us that D of T is minus 25 T plus 100. Okay, so let's keep that handy. Researcher B believes the drug behaves like caffeine and decays exponentially. And so in exponential decay, we would have D dash of T is equal to minus KD, where K is positive. Okay, so let's solve this differential equation. Well, we already know what this looks like. It's separable. We divide both sides by D, integrate. And so we're going to get D of T is a constant A times e to the minus KT. Now, with D of 0 is 100, we have 100 is equal to A e to the power of 0, which is A. And so that says A is 100. And so this gives us D of T is 100 e to the minus KT. Now, using D of 1 is 75, we have 75 is equal to 100 e to the minus KT, but T is 1 in this case. So this gives us e to the minus k is equal to 0.75, which is 75 over 100. And so then minus k is the natural log of 0.75. And so k then is equal to minus natural log of 0.75. But there's a log rule that says we can take that minus 1 into the exponent and call this the natural log of 1 over 0.75. Now 0.75 is 3/4, so this is 4 over 3 when we invert 0.75. Okay, and so opening up Mathematica here, let's estimate this. So natural log of 4.0 over 3 is approximately 0.2877, let's say, putting that to 4 decimal places. Okay, so let's go back to our question, give its general solution, and use the information to determine d of t. Okay, so then we found d of t is a e to the minus kt, but a is 100, so 100 e to the minus 0.2877 t. Now, for the part of this question that asks about the half-life, d of t is 1/2 d of 0. And so 1/2 d of 0, because d of 0 is just a, and we know a is a 100, so 1/2 of 100 is 50. What we want to do with this is solve for t to get the half-life. And so this would say 100 e to the minus 0.2877 t is 50. So dividing both sides by 100 and taking the natural log, we have minus 0.2877 t equals natural log of 0.5, or 50 over 100. Okay, and so multiplying both sides by minus 1 and bringing that up into the exponent, we have 0.2877 t is equal to the natural log of 2. And so the half-life t is natural log of 2 over 0.2877. Okay, so let's estimate this using Mathematica. And so we have half-life is 2.41 hours, because this was in hours. Okay, so this says that half of the drug is out of the system after 2.41 hours. Okay, question 6. So find the particular solution of dx on dt is x squared cos of t with x of 0 is 1. So this equation here is separable. So we divide both sides by x squared. So we have the integral of x to the minus 2 dx is the integral of cos of t dt. And so we want to integrate both sides. Now that exponent 2 is not equal to minus 1, so we add 1 to the exponent and get minus 1, divide by the new exponent, and so 1 over minus 1 is minus 1. So we have minus x to the minus 1 on the left, plus c, but we'll put the c on the right-hand side. We don't need two of them. The integral of cos of t is sine of t, and then we have plus c. All right, so multiplying throughout by minus 1, 1 over x is minus sine of t plus some other constant. Let's call it b. It's just minus c. Okay, and so now we want to invert both sides. So we get x as a function of t. So x as a function of t is 1 over b minus sine of t. Okay, now with x of 0 is 1, we have 1 is equal to x of 0, which is 1 over b minus sine of 0. And so this is 1 over b because sine of 0 is 0. So b is equal to 1, which gives us x of t is 1 over 1 minus sine of t. Okay, now question 7 says an organism of length L has a surface area proportional to L squared. If we assume that its growth rate is also proportional to its surface area, we can model this as the L on dt is k L squared, where k is the constant of proportionality. So L of 0 is 1. How long does the length vary with time? All right, so we have this initial value problem. This equation is separable, so let's divide both sides by L squared. We have L to the minus 2 dl integrated is the integral of k with respect to t. Okay, and so integrating the left-hand side gives us minus 1 on L. On the right-hand side, we have kt plus a constant c. Now, since L of 0 is 1, that says when t is 0, L is 1. So since L of 0 is 1, minus 1 to the minus 1 is k times 0 plus c. And so we see that c is minus 1 because 1 to the minus 1 is 1. So minus 1 to the minus 1 is minus 1. So c is minus 1. Okay, and so this gives us minus 1 over L is kt minus 1, multiplying throughout by minus 1 and inverting gives us L as a function of t is 1 over 1 minus kt. All right, question 8 says find the general solution of dy on dx equals x squared y cubed. Now this equation is separable, so let's put the x with the x and the y with the y. So y to the minus 3 dy equals x squared dx. Integrating this, we have minus 1 over 2, y to the minus 2 is 1/3 x cubed plus c. Okay, so multiplying throughout by minus 2, 1 on y squared is minus 2/3 cubed plus some other constant, let's call it k. Now solving for y squared, we just invert both sides. So we have y squared equals 1 over k minus 2/3 x cubed. All right, and so now taking square roots will give us two solutions. Y equals plus or minus the square root of 1 over k minus 2/3 x cubed. So in 9a, we have the initial value problem. P dash is 2p minus 5, where p of 0 is 3. So this equation is separable. It's also linear, but let's solve this as a separable equation. So separating this, we have dp over 2p minus 5, 1 dt. Okay, so integrating this, now when the derivative of the denominator is the numerator, then we have the natural log of that denominator, but it's not quite here. And so we can pull out the 2 so that that becomes the case. So let's factor out a 2 out of that denominator, and then in front appears a 1/2, p over p minus 5 over 2. We can do that. And so on the right-hand side, we just have t plus c. Okay, now on the left, we have the natural log of p minus 5 over 2. So 1/2 natural log of p minus 5 over 2. And on the right-hand side, we still have t plus c. Okay, now multiplying throughout by 2 gives us natural log of p minus 5 over 2 is 2t plus b, where b is equal to 2c. Now let's solve for p minus 5 over 2. So e to the power of 2t plus b, which is e to the b times e to the 2t. Now let's name that e to the b. Let's name it a. So solving for p, we have p as a function of t is 5 over 2 plus a e to the 2t. Okay, so now this is an initial value problem. So we'll say since p of 0 is 3, that says when t is 0, p is 3. So we have 3 is equal to 5 over 2 plus a e to the 0. E to the 0 is 1, and so we have a is equal to 3 minus 5 over 2. And so this is 6 over 2 minus 5 over 2. So we've got 1/2. Okay, now using that up in here, thus p of t is 5 over 2 plus 1 over 2 e to the 2t, and we can factorize out a 1/2 and write it like that. All right, let's go to part B. So 9 part B, y dash is 2 minus 3y, y of 1 is 0. So this is both linear and separable. Let's take that 3y over to the left-hand side and solve this as a linear equation. Okay, so our integrating factor, I of t is e to the integral of 3 with respect to t. So we have e to the 3t. So multiplying throughout by e to the 3t, the left-hand side will pack up using the product rule as the product of the integrating factor times y. And on the right-hand side, we have 2 times the integrating factor. Okay, and so now integrating both sides, e to the 3t times y is the integral of 2 e to the 3t with respect to t. And so this integral is 2/3 e to the 3t and then plus a constant c. Okay, so now dividing throughout by e to the 3t, we have y as a function of t is 2/3 plus c e to the minus 3t. So now let's use y of 1 is 0. So we have 0 is equal to 2/3 plus c e to the 0. So that says that c is minus 2/3. And so y of t is 2/3 minus 2/3 e to the minus 3t. Okay, question 10. We are looking at equilibrium solutions of various differential equations. So remember, an equilibrium solution is where the derivative is equal to 0, but it's not just temporarily, it's for all time. Okay? So an equilibrium solution is an actual trajectory to the differential equation. So 10a p dash equals 3p minus 5. So what we do here is we solve for this equal to 0, because if this is 0, then p dash is 0. And so solving this is easy. We take the 5 over and divide by 3. So p is equal to 5 over 3 is our equilibrium solution there. Now, it doesn't have a t in it, so it's indeed an equilibrium solution. It is a trajectory of the differential equation. Okay, so part B, y dash equals 1.2 y plus 12. Okay, so we solve this equals 0. Take this over to the right-hand side, divide by 1.2, so we have y equals 12 or minus 12 over 1.2, which is minus 10. Again, it doesn't have any t's in there, so it's an equilibrium solution to that differential equation. Okay, part C, dA on dt is 2. Okay, this has no equilibrium solutions because this is never 0. So no equilibrium solutions. Okay, part D, dx on dt is 3x squared minus 2. All right, so solving for this equals 0, take the 2 over, divide by 3, so we have x squared is 2/3. Take square roots, and you have the two solutions. X is plus or minus the square root of 2/3. Okay, now part E, dp on dt is cos of p. So when is this 0? So cos of p is 0. Well, if p is equal to pi on 2, then we get 0, but it's actually pi on 2 plus all integer multiples. So p is pi on 2 plus k times pi, where k is an integer, whole number. Could write is an element of the set of integers. So in brackets here, I'll put k. All right, part F, dq on dt is e to the minus q minus q. Okay, so when do we have that equal to 0? So e to the minus q equals 0. Well, for this one, you would probably want to solve for q numerically because this is a nonlinear equation. Okay, so let's seek out a numerical solution. I'll open up Mathematica for this. All right, so I'll define a function of q. And so I'm looking for zeros of this function. So I've just built a function of q representing the left-hand side there. Let's plot this. Okay, so we can see it looks like it crosses the axis somewhere here at a number q less than 1. So how about we run Newton's method, if I can remember how that goes. So I need to write a function g, so q minus f of q over the first derivative of f. Okay, now differentiating that function f with respect to q, we have minus e to the power of minus q minus 1 as the first derivative. And so I'm going to call that g. So now what we want to do here is write an update procedure. Now I'll just use table to do this. That's the easier way than writing a for loop for this. So x equals g of x. Okay, then above that, I'll come up here and write x equals 0.5 is a reasonable guess. And we'll tabulate this for, say, 10 terms over some letter j. Okay, let's have a look. So these get closer and closer to the zero of the function where it crosses the q-axis, the horizontal axis. And so you can see these look to be converging. So q equals 0.5671, etc. by Newton's method, which is what I just used in Mathematica. Okay, so that's an equilibrium solution to this. All right, let's move on to question 11, which says find equilibrium solutions to the equation dq on dt is 0.6 q minus 3.0 and determine its stability. So let's find the equilibrium solution first. So we want to solve 0.6 q minus 3.0 equals 0. Take the 3 over to the right-hand side and divide by 0.6. So we get q equals 3.0 over 0.6. Now that's 3 over 6/10. So I multiply top and bottom by 10. So we get 30 over 6, which is 5. All right, so q equals 5.0 is our equilibrium solution. Okay, now the next part of this asks us to determine the stability of this. And so what that means is, so let's draw a picture of this first. So here we have our equilibrium solution. Q is 5. Now that's a trajectory. Other trajectories do not cross this equilibrium solution, as in other solutions to this differential equation up here. They do not cross this equilibrium solution. So the stability of this asks the question, do other trajectories tend towards this equilibrium solution, or do they tend away from it? So what I like to do for these is, because we only have one equilibrium solution, put in brackets unique, I'll just choose a number that is less than that equilibrium solution. So I'll say choose, and just in aid to tell you what's going on, choose 4, which is less than 5. Okay, and then let's just take that 4 and sub it into this differential equation there. So q dash of 4 is 0.6 times 4 minus 3. Okay, 6 times 4 is 24, so this is 2.4 minus 3, and so we can see that is negative. So then I'll just make a statement, because it'll work for other numbers too that are less than 5. So I'll say for all q less than 5, the q on dt is negative. Okay, and similarly, for all q greater than 5, and to decide this, you can just choose 6, which is greater than 5, sub it in here. You get 3.6 minus 3, which is positive, okay, which gives you an idea of what's going on in general. So in this case, when q is greater than 5, dq on dt is positive. Okay, so then I come up to my diagram and I draw a picture of this situation. So if we have negative slope, well, that looks like this. And when we have positive slope, that looks like this. So this is unstable because trajectories are tending away from that equilibrium solution. So that's an unstable equilibrium. All right, question 12. So in part A, we have 2 dy on dt minus y minus 1 times y minus 5 is 0. Let's take this over to the right-hand side and divide by 2. So we can write y dash equals 1/2 y minus 1, y minus 5. All right, so solving for when this derivative is 0, we have y equals 1 or y equals 5. These are our two equilibrium solutions. So let's sketch this, the 1 and then say 5 up here. Okay, so we have 3 regions. let's identify these. So region 1, all numbers up to 1, region 2, and region 3. So let's choose a number less than 1 so that it's in region 1, and let's evaluate the sign of y dash. So we'll say if y is less than 1. Now, you can just choose 0 to make this easy for yourself to look at the sign. So if we chose 0, then we'd have minus 1 times minus 5 is plus 5 times 2. That's positive. So we'll say then y dash is positive. Okay, so let's draw a picture of that. Arrows or trajectories going towards that equilibrium solution. Okay, now next, if y is greater than 1 but less than 5, now let's think of a number, an easy number. Let's choose just y equals 2, for example. So if we chose y equals 2, then this is positive and this is negative, meaning that product there is negative. Negative number times a half is negative. Okay, so trajectories going towards this equilibrium solution in region 2 and away from the y equals 5 equilibrium solution. All right, so if y is greater than 5, then let's choose a number, say 6. 6 minus 1 is 5, that's positive. 6 minus 5 is 1, that's positive. So we have a positive y dash. Okay, and so trajectories go up and to the right. So that's away from the trajectory y equals 5. Okay, so this one, y equals 5 is unstable because trajectories go away from that solution. This one here at y equals 1 is stable because trajectories go towards it. All right, part B. dp on dt is cos of p. Okay, so we already determined that the equilibrium solutions of this were pi on 2 plus an integer times pi. So these are our equilibrium solutions here, but which ones are stable and which ones are unstable? So if we choose k is 0, we have p is pi on 2. And so if I add another pi on 4, so cos of pi on 2 plus pi on 4, what's the sign of this? So this is cos of 3 pi on 4. Okay, now which quadrant is 3 pi on 4 in? So pi on 2 is there, and then 3 pi on 4 will be here. So that's the second quadrant. So cos is negative there. And so if p is greater than pi on 2, but less than pi on 2 plus pi, which is 3 pi on 2, then p dash is negative. Okay, now let's do the same thing in the next section. So if I evaluate this at 3 pi on 4 plus pi, then we have 7 pi on 4, which is in the fourth quadrant. So in that case, cos will be positive. Okay, so if p is greater than pi plus pi on 2, but less than 2 pi plus pi on 2, then p dash is positive. And so we have alternating stability. All right, so let's draw a little diagram of what we have so far. Okay, so pi on 2, and then up here let's put pi plus pi on 2. Okay, so we said if it's in here, then we have a negative slope. But if it's in here, we have a positive slope. Okay, so that tells us that this is unstable. This one is going to be stable, and these are oscillating in their stability. All right, so let's move on to question 12c. So in 12c, we have dp on dt is p cubed minus 3p squared plus 3. Okay, now let's open up Mathematica to try to factorize this. Okay, so it doesn't give us any nice integer factors. So now let's try to solve numerically, but I'll just use a shortcut here. I'll write n solve and I'll put equals equals 0. So we have one real solution minus 2.1038, and that's the one we're interested in here. Okay, so we'll say one real equilibrium solution at approximately minus 2.104. Okay, and so now if we replace, take this, and I'll write replace all with this little shorthand. P goes to minus 2. Now minus 2 is greater than minus 2.1. Okay, so at minus 2 we have a positive slope. So we'll say if P is greater than minus 2.104, then P dash is positive. Okay, now let's replace this with a number below that. So if P is less than minus 2.104, then P dash is negative. Okay, so let's draw a picture of this. So here's our equilibrium solution here, minus 2.104. Okay, and so if it's above that, then we have a positive slope, or positive slopes of trajectories. If it's below that, we have negative slopes of trajectories. So this equilibrium solution appears to be unstable. All right.